Hello and good morning, grade 9 with you, Mr. Samir Awad, and today we are going to start electrons arrangement of in atoms part 2. And we start part 1 with the three principles we said about, and the after that the exclusion principle, and after that we get to start today Hans rule. We get a little hint about it, but let's start today. So as we said, Helm's rule is going to occupy the electrons first singly at the orbitals of the same energy or equal energy as follows, and after that start to pair them. Just for example, in the p orbital. So if we have three electrons here, we'll put them singly first, and after that, the fourth one will be occupying as a spinning here, opposite spinning pairing here. If I get 5, I will put another one. If I got 6, I will put another one here or to pair. But first of all will be singly. Like you see here, guys, the orbitals for hydrogen is getting to be in 1s, 1 electron will be here. But if I get 2 electrons here in helium, so I will start to put the first one here, and after that I will pair. For example, here for lithium, I have 3 electrons. I will put the first one, and the second one will be paired, and after that I will get to the other orbital of different energy to build single electrons. So here carbon is getting to have 6 electrons, so we'll put the first 2 in 1s2 to be filled, and 2s will be 2s2 filled with 2 electrons. And when I get to the p, I have 3 orbitals of the same energy, so I have 2 electrons. I will put them not paired, I will put them singly, as you can see. So if we get to nitrogen, it will be more illustrating here. 7 electrons, 2 at 1s2 and 2 at 2s2, and we will get 3 electrons at B, so 2p will be 2p3. I will put them singly, 1, 2, 3, not 2 and 1, no, they will be single first. But look at the oxygen, we'll get to have to do 1s2, 2s2, and 2p4, so we'll put single electrons first, and the fourth one will start to be paired here. And for fluorine, the same, but I will pair the second one too. And for neon, I will pair them all, as you can see. So the 1s orbital has 2 electrons of opposite spin, and also the 2s orbital has 2 electrons of opposite spin. And when I get to each of the 3 of 2p orbitals has 1 electron, the remaining electron now pairs with an electron occupying one of the 2p orbitals here. So a convenient shorthand method for showing the electron configuration of an atom involves writing the energy level and the symbol for every sublevel occupied by an electron. So you indicate the number of electrons occupying that sublevel with the subscript. For hydrogen with 1 electron in a 1s orbital, the electron configuration will be written as 1s1, so the superscript will be the number of electrons here. For oxygen with 2 electrons in a 1s orbital and 2 electrons in 2s orbital and 4 electrons in 2p orbitals, the electron configuration will be shorthanded simply as 1s2, 2s2, and 2p will get 4 electrons. Note that the sum of the subscripts equals the number of electrons here, or superscript, sorry, will be equal to the number of electrons in the atom here. So the number of electrons in the oxygen will be 2 plus 2 plus 4, it will be 8 electrons. So explain why the correct electron configuration of oxygen is 1s2, 2s2, 2p4, and not 1s2, 2s2, 2p3, 3s1, because according to Hund's rule, we start to put the electrons singly first for the equal energy orbitals, like in 2p. So I will put the 3 first, and after that I will pair the extra electrons after. So the 2p orbitals are lower in energy than the 3s orbital, so they will be completely filled before any electrons will be found in the 3s orbital. So writing electron configuration here, the atomic number of phosphorus is 15. Write the electron configuration of a phosphorus atom. So it will be, as we say, 1s, 2, 2s, 2, 2p6, and 3s, 2, and 3p3. So the phosphorus has 15 electrons, as you can see, guys. So according to above, we'll start by the electrons of the orbitals of lower energy, 1s2, 2s2, 2p6, 3s2, and 3p3. So the overall for them will be 15 electrons. The superscripts, when I collect them together, will be for me 15 electrons here. So exceptional electron configuration, you can obtain correct electron configurations for elements up to vanadium by the following about diagram orbital filling, guys. But here we have two exceptional, configuration for, here you can see in chromium and in copper, because here, 3D is going to have 9 electrons and 3D is going to have 4 electrons here if I bought it in the normal configuration. But exception here, that 1 electron of 4s is going to jump here to 3D in order to make it more stable by half filled electronic configuration 3D5. And 1 electron here from copper, will move from 4s2 to 3d9 to make it 3d10, and 4s1 to be fulfilled with electron 3d10. So that is going to be exceptional for them, and that arrangement needs to make them more stable by half filled the sublevel or fulfilled, the sublevel for copper and chromium. Some actual electron configurations differ from those assigned using the above principle, because although half-filled sublevel are not as stable as filled sublevel, they are more stable than the other configurations. So here, let's get an example. What is the correct electron configuration of sulfur here? And sulfur has 14 electrons, I think. No, it has 16 electrons. So 16 electrons we'll get by the end. 1s2 to s2 to p4. It cannot be 4, it must be 6. 1 s2 to s2 and 2p6, that's 10. And 3s2 and 3p3, that's 15 electrons. And 1s2 to s2 2p6, that will be 3s2 and 3p4. That's the perfect configuration, so number C will be the answer for it. So we got 3 rules, guys, by the end of Pauli principle, the Pauli exclusion principle, and Horn's rule tell you how to find the electron configurations for the atom. Thank you for listening, guys. Get back to study well, and good luck. Be safe at home.